Hello. In this video, I'd like to continue our unit on acid-base chemistry by talking about the pH scale. Now, we learned in the previous video that the acidity or basicity of a solution can be quantified by specifying either the hydrogen ion concentration or the hydroxide ion concentration. So, if I give you a solution and I tell you either of these concentrations, you know not only whether it's acidic, basic, or neutral, but also exactly how acidic or basic it is. An acidic solution is one in which the hydrogen ion concentration is greater than 1.0 times 10 to the negative 7th molar, and because the hydrogen ion concentration and the hydroxide ion concentration are inversely proportional, the hydroxide ion concentration is less than 1.0 times 10 to the negative 7th molar. Correspondingly, we know it's a basic solution if the hydroxide ion concentration is greater than 1.0 times 10 to the negative 7th molar, and therefore the hydrogen ion concentration is less than 1.0 times 10 to the negative 7th molar. What is the significance of that value, 1.0 times 10 to the negative 7th molar? Well, you'll recall that is the concentration of both the hydroxide ion and the hydrogen ion in a neutral solution. Now, these numbers are very, very small, and using scientific notation can sometimes be cumbersome. So to simplify very small numbers, scientists decided to use the logarithmic scale, which of course is the pH scale. pH means the power of the hydrogen ion concentration. I only actually learned that a few years ago. And pH is defined as the negative of the base 10 logarithm of the hydrogen ion concentration. So, if you know the hydrogen ion concentration of a solution, you simply take the base 10 logarithm of it, and because the hydrogen ion concentration is less than 1, that will be negative, change the sign to make the pH positive. So, if the hydrogen ion concentration is 1 molar, which is quite high, the pH will be 0.00. That corresponds to an acidic solution. If the hydrogen ion concentration is 1.0 times 10 to the negative 7th molar, the pH will be 7.00. That is a neutral solution. And if the hydrogen ion concentration is very, very small, 1.0 times 10 to the negative 14th molar, the pH is 14.00, and that is a basic solution. Okay? We rarely talk about solutions in which the pH is less than 0 or greater than 14. The theory of aqueous solutes kind of doesn't work under very, very high, very, very low concentrations. Okay? The pOH scale is a scale for the basicity, and as you would suspect, it means the power of the hydroxide ion concentration, and it works pretty much the same way. The pOH is the negative base 10 logarithm of the hydroxide ion concentration, and the same thing applies. Essentially, a low value of px means a relatively high value of x. So a low pOH will mean a basic solution, a high pOH will mean an acidic solution. Now, on the previous slide you saw how to calculate the pH or pOH given the concentration, but how do you go in the reverse direction? How do you calculate the concentration given the pH or pOH? Well, here we're going to use our rules of logarithms. If pH is the negative base 10 logarithm of the hydrogen ion concentration, then the hydrogen ion concentration is 10 raised to the power of the negative pH. And if the pOH is the negative base 10 logarithm of the hydroxide ion concentration, then the hydroxide ion concentration is simply 10 to the negative pOH. Now, as you might guess, there is a distinct relationship between pH and pOH. Let's see how that works. We'll begin with the Kw expression. Kw equals the product of the hydrogen ion concentration and the hydroxide ion concentration. If I take the negative base 10 logarithm of both sides, negative log of Kw, that will be equal to the negative base 10 logarithm of the product of the hydrogen ion concentration and the hydroxide ion concentration. Well, the right-hand side is simply equal to the negative logarithm of the hydrogen ion concentration plus the negative logarithm of the hydroxide ion concentration. Well, that's simply equal to pH plus pOH by definition. Well, Kw has a numerical value, 1.0 times 10 to the negative 14th, so I can actually evaluate that. The negative base 10 logarithm of 1.0 times 10 to the negative 14th is simply 14.00. So this gives me a very simple quantitative relationship between pH and pOH. Just as the hydrogen ion concentration and the hydroxide ion concentration multiply to give Kw, pH plus pOH add to give 14.00, which makes perfect sense mathematically. So let's do some exercises. The acidity or basicity of a solution can be quantified using any one of 4 quantities: pH, pOH, the hydrogen ion concentration, or the hydroxide ion concentration. For the following solutions, calculate the other 3 and state whether the solution is acidic, basic, or neutral. Now, one important question is, do you need to do any calculations before determining whether it's acidic, basic, or neutral? And the answer obviously is no, you don't. You can simply use the numerical value of any of those four quantities, compare it to a neutral solution, and determine whether it's acidic, basic, or neutral. So in the first case, we're given a solution that has a pH of 9.63. If the pH is 9.63, that means the hydrogen ion concentration is less than 1.0 times 10 to the negative 7th, which means that it's going to be a basic solution. There are numerous ways you can go from one of these four quantities to the other. Choose the one that's most convenient for you. I'm going to begin by calculating the pOH as 14.00 minus the pH, which is 14.00 minus 9.63, or 4.37 as my pOH. Notice that the logarithmic quantities, pH and pOH, are unitless quantities, and we customarily represent them with 2 digits after the decimal point. To calculate the hydrogen ion concentration, I will choose to use 10 to the negative pH, which is straightforward. 10 to the negative 9.63 is 2.3 times 10 to the negative 10th molar as my hydrogen ion concentration. Remember, concentrations need to have units of moles per liter, and by custom, we express concentrations with 2 digits after the decimal point. To calculate my hydroxide ion concentration, the final value, I can do one of two things. I can either do 10 to the negative pOH, or I can do Kw over the hydrogen ion concentration. Choose whichever one's easier. You'll get the same answer either way. I'll choose the latter, 1.0 times 10 to the negative 14th, my Kw value divided by the hydrogen ion concentration, 2.3 times 10 to the negative 10th, is equal to 4.3 times 10 to the negative 5th molar as my hydroxide ion concentration. And notice that each of the three quantities I just calculated is also consistent with the solution being basic. For my final example, I'm given a hydroxide ion concentration of 5.4 times 10 to the negative 10th moles per liter. Because the hydroxide ion concentration is less than that of neutral water, I know that the hydrogen ion concentration has to be greater than that of neutral water. That is consistent with it being an acidic solution. So let's calculate the remaining quantities. The hydrogen ion concentration is Kw over the hydroxide ion concentration, or 1.0 times 10 to the negative 14th, divided by 5.4 times 10 to the negative 10th. Notice that because equilibrium constants are unitless, I'm not including units in my calculation, but I am including units in the final result. And I get 1.9 times 10 to the negative 5th molar as my hydrogen ion concentration. Again, smaller than that of neutral water, greater than that of neutral water, therefore consistent with an acidic solution. My pH, I'll take as the negative base 10 logarithm of the hydrogen ion concentration, or the negative base 10 logarithm of 1.9 times 10 to the negative 5th, or 4.73 as my pH. And then finally, to calculate the pOH of the solution, again, I can do it one of two ways. I can either take the negative base 10 logarithm of the hydroxide ion concentration, which we were given at the beginning of the problem, or 14.00, I'm sorry, back up. That should be pOH. Thanks for pointing that out. 14.00 minus the pH, or 14.00 minus 4.73 equals 9.27 as my pOH value. Once again, each of these three values is consistent with my initial conclusion that the solution is acidic. Okay, in the next video we will talk about how to calculate the pH of strong acid and weak acid solutions. See you then.